Alice. I'm a first year DPhil from the University of Oxford, and I'm going to be talking today about some of the stuff that I've been doing recently about the A01 moonquake cluster, which you can see as the red star on the picture of the moon. So this is a particularly strange moonquake cluster because it has reversed polarity events that were observed there, which is what you can see underneath the little picture of the moon. We know that moonquakes are related to the tidal stress, but the tidal stress never completely reverses direction. So there must be something else that's causing these reversed polarity waveforms. One of the options is a tectonic stress in addition to our tidal stress, or the other option is what we're actually observing at one station with these reversed events is just a rotation of the focal mechanism. So unfortunately on the moon, it's really hard to get focal mechanisms. So what we're doing is making use of the linear relationship between the Green's functions, which are the slip directions, and the moment tensor elements, which means that we can apply a latent variable analysis like principal component analysis, which is what I've tried to illustrate in this method section. So if we had a tectonic stress, that would be a pure reversal of the slip backwards and forwards, in which case we'd only have one slip direction. But if we have a rotation of the focal mechanism, it would be two slip directions. So I have some very preliminary results using the principal component analysis, which is what you can see. The first figure in the results section shows the energy taken up by each of the different slip directions. And there's a nice elbow at two components, suggesting that maybe we have two different slip directions, which is possibly a rotation of the focal mechanism causing these reversals. Thank you very much.
Okay. Thank you, Alice. That was beautifully to time. Does anyone have any questions for Alice? So maybe I can kick it off. Alice, do you have any thoughts about what the sources of tectonic stress on the moon might be?
Yeah, so there's a couple of ones that have been suggested. Things like the moon is slowly moving away from the Earth, so a readjustment to the new state as the moon moves away. But the one that's most likely is some sort of thermal stress as the interior of the moon is cooling.
Okay, excellent. And you have one more question. Are there any plans for new seismometers on the moon?
So there aren't any currently, but hopefully that would be really useful, obviously, because the original Apollo network is only 4 seismometers on the near side. What would be really great is something on the far side, but obviously that's a lot harder.
Okay, and you've got about 30 seconds, so we'll try and cram one in. Have you thought about trying independent component analysis instead of principal component analysis?
Yes, so I'm trying to fiddle around and play with both of them at the same time. Yeah.
Okay, perfect. Thank you very much. That was spot on time. So next up, we have Zahra from the University of Leeds, who is talking about intercomparisons of Sentinel-1 InSAR products. Zahra, are you able to share your screen? While she does that, actually, Charlie, are you able to stop sharing? I think officially I'm supposed to be able to do it, but I can't see which button to press. So if anyone's going over, I think you might have to be the one to do that.
Okay, that's fine. I can do that.
Okay. Or send me some instructions about which button to press. Okay.
Can you see my screen now?
Yes, that's perfect, Zahra.
Okay. As you might aware, European ground motion service is under development to deliver ground motion over Europe using Sentinel-1 data, probably processed by different InSAR suppliers. So these different InSAR providers can produce products that can be dissimilar in terms of different metrics. So there is a need to ensure the consistency between different InSAR processing methods, and our main goal in this project was presenting and testing a fair and robust method to assess similarities and differences between different InSAR methods. So our proposed method is based on a Terraform validation project, but tackles its limitation. It compares geo-coded data with no assumed reference InSAR product and is open to any InSAR methodologies. It can split to pre-processing and intercomparison stages. and it compares different metrics like velocities, time series, density and coverage, and also some qualitative metrics. We used Sentinel-1 InSAR data over an area in Glasgow using 4 different InSAR methods, and extracted some statistics from velocity and time series differences to assess the agreement between each 2 InSAR products. Also, the InSAR results were comparable, but there were considerable differences in some aspects. So we discussed the major differences in this research and the main reasons for them, and recommend some requirements for any national, international InSAR products. So for more details, please refer to our preprint paper, which I uploaded to the Slack channel. Thank you.
Great. Thank you very much, Zahra. Could you stop your screen share?
Yeah, sure.
Thanks. Does anyone have any questions for Zahra? So maybe I can get the ball rolling again, Zahra. So you've just tried this on one test site so far. Do you have plans to expand to other areas?
Yeah, it's a suggestion in this project because we had some limitation with our test site. The deforming area was very local, and also we didn't have access to any ground truths. I mean, any independent measurements. So it's very good to have access to multiple different InSAR data in a network of test site with different applications, and also with having access to some ground-based measurements like dense network of GPS or leveling measurements or even corner reflectors. Yeah.
Okay. Excellent. No other questions yet, so I guess I'll ask another one. So you mentioned the European Ground Motion Service. Do you have an idea of when that might be released? Do you know what's the timeline for that?
No idea. I know that some of the countries like Italy, Denmark, Spain, some of these countries are in the progress of preparation, but no, to be honest, I don't have any idea about that.
I think this comparison is going to be a big challenge for a service like that. So I think they've got a lot of work to do. Okay. Okay. Oh, quick question from Ekbal. What reference frame will they use? Will it be ITRF?
Sorry, what reference will they be using? The ITRF or? I think it was ITRF. Yeah.
Yeah, I'm not sure they've decided yet, actually. So it's a good question, though. All right, we should now move on to the next one. Thank you, Zahra.
No
next
problem.
up is Edna, also from Leeds, who is looking at radar backscatter analysis from Kīlauea. Edna, are you able to share your screen?
Yeah, can you see that now?
Still coming? Yes.
Okay.
Perfect.
So this is some of the work I've been doing over the last few months, which has been using satellite-based radar backscatter to examine the Papua crater in Kīlauea during the 2011 to 2013 eruption, in particular looking at the inflation and the collapse of the crater itself, and then looking at the variations of the active lava lake. So I've been using the radar shadow, which is a shadow produced by the side-looking nature of the satellite to calculate the height of the crater floor with respect to the top of the crater rim. And you can see in this animation of the crater itself, you can see how the shadow size changes over time. We found, though, that not all the cross sections that cover the crater shadow were able to pick out the changes in the motion of the crater floor, as the shape and size of the shadow itself is controlled by the dimensions of the crater and the angle of the satellite look direction. So some of these factors caused some reduction in the heights we were able to calculate, which you can see in the blue and the black plots here. However, overall, we were able to see some good correlation between the different sections, and especially when the crater was quite shallow. Overall, we were able to see the collapse of the crater quite nicely, the inflation between the different events, and then this maintained inflated crater during the third eruption of that period. We also had a look at the variations in the active lava lake throughout that time, and currently examining different ways of identifying when the lava lake is present, and then how to extract the shape from it. So currently we're doing this by looking at the data distribution, looking at different variables, and using cluster analysis to pick out the shape. And the idea here is possibly to correlate the changes we see in the radar backscatter and compare that to the surface roughness, as this should tell us something about the convection of the lake at that time. So a few things I still want to do is extend the time series in both directions to get a better idea of what was happening before and after, and as well correlate the information and observations I have with what was happening in the flow field and the lava flows at that time. Thank you.
Thanks. We have a question lined up already. Several questions. Are there plans to correlate with InSAR or other ground deformation gravity to get information on pressure within the East Rift Zone?
Yeah, so at the moment I've just been doing just on the backscatter, but the idea is to combine it with the other data sets that there are, because there's plenty on Hawaii, and see what correlations there are and what information we can see from that.
Okay, and Pablo asks, does the speckle noise help to estimate, or is it useful to despeckle the backscatter images?
So I've got a filter on for speckle, which it seems to help at least with identifying where the edges of the crater. It makes the image a bit clearer and helps with the cluster analysis and stuff like that. So it seems to be helping. I have to play around with a few other ones still.
Okay. Oh, questions are flooding in. From Brendan, is this method well suited to craters of differing geometries, e.g. wide or shallow versus small and deep?
So it's definitely something to consider. So I've had a few of the issues I've had with Papua is when the crater collapses very deeply, sometimes the shadow interacts with the other side, so you don't actually see the complete depth. So there is a cutoff with definitely smaller ones. So I guess wider ones might be better and that suited for that. But yeah.
Okay, and from Chris, are there any feedback relationships between the level changes at Pu'u and the summit lava lake? I guess that would be on your correlation.
Yeah, so I haven't looked at the summit one at the moment, but from reading and stuff, there is always correlation, a lot of links between the two, and there's been a lot of work done on the summit and the summit lava lake using different methods as well. So it'd be interesting to look at the correlation there.
And very quickly, Philippa would like to know what in situ ground observational measurements are there to correlate with these?
So at the moment, I have to look into. I've got the HVO like daily reports, so they've got all the field observations and stuff like that. But they've also got GPS and then a lot of webcam tilt measurements to look at different thermal properties and variations like that. So still have to go through a lot of that.
Okay, yeah, I think there's a lot of data there. All right, thank you very much, Edna. We will move on. Next up is Brendan from Manchester, who's going to talk about gas chemistry at Bagana.
Okay, hi folks. It's really nice to see you all. My poster is in the Slack channel. I'm just going to present now with a few quick summary slides. So Bagana is among the youngest and fastest growing volcanoes on the Earth, and one of the largest emitters of sulfur dioxide gas. So ranked number 3 in the world over the last decade or so, based on satellite observations. It's been hypothesized and recently predicted using relationships between volcanic gas chemistry and whole rock trace element chemistry that Bagana should also be among the largest global sources of carbon dioxide. We can't reliably measure CO2 emissions from space, so we went into the field. We place a gas sensor payload aboard a drone. We launch it by hand about 7 kilometers from the volcano, and after getting to altitude, we make a few passes to and fro in the summit gas plume. Simultaneously, we've got a ground-based team who measure SO2 flux using optical spectroscopy, so either a UV camera or a spectrometer, sort of zenith pointing, mounted on a second drone. The SO2 fluxes we measure converge around a few hundred tons per day, and this is surprisingly low, around an order of magnitude below the decadal mean emissions inferred from the satellite observations. And the gas composition data measured by the aircraft-mounted drone gives us a reasonably widely varying CO2 to SO2 compositional range. So we're still working on analyzing the spatial variability in these ratios, but a picture is emerging of lower carbon to sulfur ratios that is potentially more magmatic directly over the summit rather than off axis. We're interpreting the low SO2 flux and generally high carbon to sulfur ratios as a result of scrubbing, that is rising gas interacting with groundwater, so rain in a very porous edifice. And this is quite a common process at quiescent volcanoes and is essentially our bad luck in the timing of our fieldwork at this otherwise relatively highly active volcano. But just to conclude then, Bagana may be a major global emitter of volcanic deep carbon, but the current data are inconclusive. So the key point I want to emphasize is this study illustrates the stochastic nature of volcanic emissions and how perhaps as a community we've been making a bit of a mistake in reducing study of these volcanoes to individual fluxes, individual compositions. We're writing the paper emphasizing the need for more dynamic emissions inventories, and satellites and drones both offer potential paths to the volume of data we need to pursue that goal.
Excellent. Thank you very much, Brendan. I have a question coming in already from Tamsin. Could you use the drone to map fumaroles and surface alteration that might be evidence of diffuse CO2 emissions?
Yes, I think we could. So we weren't purposefully doing that, but we have a lot of footage gathered from several flights over the summit. So we are going to look at putting something together. The problem really, I think, is the summit itself has so many points of gas escape that we're struggling to see it coherently through the emissions themselves. It's not that there is a single kind of neat plume emanation point. There's multiple points of emission all over.
Okay, from Colm, great presentation. What is the accuracy precision of the drone sensor?
The accuracy and precision is good. So I mean, like fractions of a ppm. The problem we have in terms of the data quality, I think, is the amount of the residence time in the plume is not particularly long. So if we were on the ground, ideally we would be leaving the instrument there to be swept by the plume for long periods of time. And definitely a challenge in this method is how reliable what the short observation windows actually are to that kind of stochastic variability on a shorter term.
Okay, quick one from Tim. Did the satellite data from the same time as the drone also show low values?
Yeah, so we have seen in the months before and after that Bagana is currently in a low state of activity, and this is definitely informing our interpretation. So we have some internal Manchester funding at the moment, and we're looking in more detail at Tropomi data. So Kat Hayer's leading this work. So hopefully we can report back soon. We're not necessarily going to go down the kind of ground truthing route, but I think we can do. We can show that the fluxes we measure in the field and the fluxes we're retrieving from space are close to each other, I think.
Okay, so we're going to try and keep things current. So there are a few more questions and comments both about this talk and about previous ones that are turning up in the chat. I'm not going to read those ones out now, but everything will be put on Slack by Chris later. So please do keep chatting about these things in that medium. So we're going to move on now. The next up is Daniel Gittins from the University of Oxford. Automatic detection of surface creep events on the San Andreas Fault. Daniel, are you ready?
Yeah. So over the last couple of months, I've been looking at the creep meter records for the San Andreas Fault to try and find these things called creep events, which are parts of accelerated slip at the surface. So I tried doing this manually to start off with, but soon realized that picking thousands of creep events from more than 20 creep meters was probably not a viable way to go. So I decided to try and do it automatically. So I used a cross correlation technique by using a template creep event, which is here in red, to look and see if I can find these creep events in the creep record. So underneath this little figure here is the 2D histogram of the cross correlation peak. So the peak where cross correlation is highest plotted against the total slip in the next 24 hours after these peaks. and we expect any creep events that we're going to find are going to fall in this blue region here, where we have a high cross correlation value and a large amount of slip. So got this running the last couple of weeks, and some preliminary results came out. So we've managed to find in total 113 creep events from 1 creep meter. Using this, there's still some errors in the timing. They might be a bit earlier, a bit late, but overall it seems like it's going to help to find these creep events, which would be useful, because once we've found them, we're hoping to, for further work, to look at the characteristics of these events and try and find out how big these creep events are and how far they propagate along the fault. So,
Okay,
yeah.
Great. We've got some questions coming in already. Do the creep events correlate with other activity, like earthquakes or nearby or anywhere else in the world?
Some of them might correlate with earthquakes nearby, but I haven't plotted the earthquake timings against the creep event timings, because I'm still trying to find all the creep events and then are going to correlate them with any earthquakes to try and find out whether it's earthquake triggered creep or whether the creep is independent of the earthquakes themselves.
I'm going to ask my own question, which was, are there enough creep meters to see if the events correlate between different creep meters?
There are in the south end of the creeping section near Parkfield. They're quite much more densely spaced than there are in the north. So you can generally see it between about, if they're within 5 kilometers of each other, you can see some propagation there from some preliminary results that I haven't presented here. But
cool. Pablo asks, what could explain the reversal of the slip motion?
in this figure here, this has been detrended. So what's happened is the slip hasn't reversed, but the detrend has taken away a larger trend than the flat sections. So this, I think this one's from a flat section here. So when you detrend it, it's just a apparent reverse slip, but isn't actually there in the actual full record. Okay.
And Luke asks, is there a change in the rate of creep after 1999? And if so, what do you think might have caused this?
There looks to be a change in rate between 99, but I'm not fully sure what has caused this yet, because I haven't probably looked into it. But there's a plan to try and work out what is causing these changes in rates over time.
Okay, I think we've come to the end of the questions, unless anything else is about to pop up. As I said, everything else will be covered within Slack anyway. So please do go to Slack and continue chatting about these things if you have questions that we didn't get around to. So we're going to move on to the final poster of this session, which is from Daniel Juncu at the University of Leeds. Volcano deformation monitoring using a sequential Monte Carlo approach. You there, Daniel?
Yeah, can you hear me?
Yep. Do you want to share your screen?
Can you see my presentation? Or?
Yep, that's perfect.
Oh, great. Okay, so I will give you some brief overview of the research I've been most recently working on. So volcano deformation monitoring using a sequential Monte Carlo approach. So this approach is quite widely used. It is very useful when you want to model time series, basically, in particular when you want to model time series as data comes in. So what this means is, in terms of the concept, is that anytime you acquire a new data point, you use this new information to update your model parameter estimates, and then moving forward, use this updated estimate as an initial estimate at the next update step when you acquire the next data. And this you can propagate this process sequentially through time without ever having to revisit the backlog of data that you have already ingested. When you looking at how this looks in action, I've got some figures of actually a case study here. Actually, that's an ongoing unrest episode in Iceland currently. Got some figures here, just the map view of some of the model results. On the top right is a GNSS time series of one of the stations, the horizontal components, east and up component, and the model fit to it. And here is an example, one of the programs that went into the processing. We used the programs from the Lixa system, so on processing system, and 2 tracks of them. So there's a lot of interprograms that go into the processing. And well, as I said before, as you ingest the data, use this to update model parameters. So what you're essentially doing is track model parameter evolution over time. So you just show some figures kind of depicting that. Yeah, thank you.
Okay. Thank you, Daniel. So Tim asks, it looks like the north component doesn't fit as well as the east components. Any ideas why that might be?
Yeah, I guess. Well, there seems to be some periodic signal that there might be not due to the source process that we're modeling here. I guess that's the reason in this case. Also, in the north component, the signal is quite low, so the signal to noise ratio is probably low as well.
Okay. I had a question about how long this takes to implement. Is it possible to do this in real time, or is this something that needs a lot of manual intervention?
Yeah, so one of the goals is basically to make this as smooth as possible. So I guess it needs some sort of interaction, but it can be basically near real time for, let's say, geodetic monitoring anyway. So basically, as soon as you get data, so the only issue is probably the time it takes to get a new data point for GNSS or InSAR, which might take a few days, unless you speed up the process, which is also possible, I guess.
Do you have to have a good idea of what the source model is before you start?
Well, yeah, you have to. There will not be as of now at least, there will not be an automatic selection of source model. So you have to try a few, I guess, and then make a user-based decision. Although this maybe somehow this could be automatized, but it's something maybe for further down the road.
Okay, that's excellent. Thank you. So I think we should probably move on to the next session. That's